Okay, so today I wanted to talk about hypothesis testing, specifically on the z-test scores for larger sample sizes. But generally, hypothesis testing is a method of statistical inference, and it's using sample data taken from a population. These tests are used to determine the reliability of outcomes from the sample data, and this information allows us to accept or reject a set of data, given that it falls within a particular deviation from the known mean. So in hypothesis testing, you need to have 5 different areas to satisfy everything to solve the problem. So first is the null hypothesis. It's usually the mean, and it's what you're trying to disprove or prove. And it comes into the conclusion at the end where you fail to reject or reject the hypothesis. Um, the second thing you need is an alternative hypothesis. That is what you're trying to prove. So if you had a mean strength that you were wondering if it was greater than, you would be trying to prove that in your alternative hypothesis that your mean is greater than that number. The third thing is a z statistic or a t statistic. T statistics are usually used for population size or sample sizes that are less than 30 or equal to 30, but in this I'm just going to be doing z statistics. The fourth thing you're going to need is a rejection region. Rejection region shows you how confident you are, and what you're trying to prove depends on basically a one-tailed or a two-tailed test. So your rejection region would be both sides of a normal distribution, and one-tailed would just basically be one side on the greater or less than for your interval. From those, you can also find a p-value, which is the rejection area outside of your main confidence interval. And then in your conclusion for the very end, you're going to have whether rejecting the null hypothesis or failing to reject the null hypothesis. And I'm going to go over all of this in some examples to make it a lot more clear and kind of distinguish what those variables are and how you use them. So the first example that I'm going to be doing is on a material's breaking strength. Okay, so in this first part, I have to just write down a little bit of the initial question that's being asked. So it says, a scientist for a metal fabrication facility has developed what he claims to be a new chemical that can alter the hardness of steel. The scientist knows that the mean hardness of the steel going to be tested is 60 HRC. So from this we know that our sample mean is equal to 60 HRC. The scientist then added his newly formed treatment to 100 individual steel specimens. So since there's 100 steel specimens, we know that N is equal to 100. And this is from the sample of the metal. And from this, of those 100 samples, we find out that the mean hardness is going to be 57.3 HRC. And that's going to be our mu naught is equal to 57.3 HRC. And it has a standard deviation of 9.5 HRC. And this is our sigma value. And this is the main data that you basically need to start out your hypothesis testing. And this, because it has a mean value that's greater than 30, is why we're going to use the z statistic for it. So the first thing that you want to do, label out what you have, and then the second thing is to create your null hypothesis. So your null hypothesis is HO. And in this, we're trying to decide if the treatment in this basically test has any effect at all. And in this test, because we're not trying to figure out if it's less than or greater than, we're just trying to figure out if it has any effect at all. We're just going to be using a two-tailed to see if it deviates anywhere from the mean. So for this, we're just going to put, for the null, the treatment has no effect. And this is because if we get the same mean value from after all these samples have been added with the solution, we're not going to have any change. So the mean is going to be exactly the same as what we started, proving that there was nothing that actually changed with the treatment. The second part that we want to do is get our alternative. So our alternative hypothesis is trying to say that the treatment has an effect. So if the treatment does not have an effect for the null hypothesis, we're going to say that our mean is equal to exactly what it was before. So in our original sample, we know that it was at 60 HRC. And then for our alternative, we're trying to say that it was anything but 60 HRC, or the mean. So our mu in this case does not equal 60 HRC. After we have these two things down, we can assume that throughout this amount of data, we can use the central limit theorem to draw our normal distribution of the data with our mean value of the sample, mu of x bar, is equal to the mu of the population of our data. So this is our 60 HRC, right in the middle. And from this, we're going to try and calculate what the standard deviation is from our sample. So the first thing that we want to do is take our standard deviation of our sample, which is here, and we can figure this out by taking the difference in our population over our deviation away. And this, since we don't know the exact population, we're going to say it's an approximate to our sample. Yeah, it's all in there. And this is the same as our sample size over n. After we add this in, we have, for our S value, that is our 9.5 HRC all over the square root of 100 samples. This value that we have, this value that we're going to have in here comes out to 0.95. And this is the deviation that we have just of the sample. So now we're going to try to find the ratio of what's going on for our actual z value. So this is more of the main equation that comes out. So our z is equal to x bar minus mu naught all over our s divided by the square root of n, which we found here. And we can plug that value in on top. So we're going to take our sample mean that we found out, which is equal to the 60 HRC. We're going to minus it from our mu naught, which is at our 57.3 HRC, giving us the difference between them, and then we're dividing it by our deviation that we found. And this comes out to 2.84, and that's how many standard deviations this is away from the mean. So both in the positive and the negative direction, we're going to find how far that is away from it. So we're looking for 2.84 this way and a negative 2.84 this way from the mean, and that'll give us our two-tailed test. So if we go, basically this would be 1, this would be 2, and this is just a little under 3. So this is our rejection region here on the positive side. Same thing on this. And and this is going to be our rejection region for our negative side. So from this z-score that we know is 2.84, we can now look it up on the table and figure out what the percentage is of this area that's all in between these two values. So because our z-score is basically this 99.77% of our total data, there's very little chance that anything's going to fall outside of what our mu naught is. At 57.3, I mean, there could be there's a 0.023 chance that it'll be outside, but it's very small. So because of this, we can say that we're going to reject our null hypothesis, which means that by rejecting it means that the treatment definitely has an effect on the metal. So he did something right. So then we'll say for our rejection region is the 0.023, and then our conclusion is that we reject the null, which is HO. Okay, so the second thing that I wanted to talk about is, since this was just saying if there was an effect or no effect in the treatment of the material, it only goes off the two-tailed test. The second thing that you can do is doing a one-tailed test to find if it's going to be greater than or less than your basically outcome. So we're going to look for in the second one on a one-tailed if we're going to have a value that's going to be less than our mean 60 HRC. So we can keep all the same data that we used for it, but we're going to have to change our null and alternative hypothesis. So our null will actually stay the same. Our mean is still going to be 60 HRC. But instead of saying that the treatment has no effect or an effect on the material, we're going to say it has less of an effect, or there's going to be less hardness in the material. So the treatment lessens the HRC. And because our alternative is what we're trying to prove, I'm going to say mu is less than 60 HRC. So now what we do, instead of looking for a two table, we're just looking for the one. So since we already know this same rejection region, it hasn't changed, we did all the same calculations to find the same z-score, but because now we're doing a one-tailed test, we're going to remove basically one of our rejection regions. So since we're looking for less than, we're going to know that we just want to reject this region at the very bottom of our normal distribution. So we'll take this back out. It's no longer going to be 99.7%, and we're just going to reject this same region down here. So now, since it's the one-tailed, we're going to take half of our rejection region, which is 0.0015. And in that rejection region, that's how much we're going to reject out of it. So now we're going to have a total confidence of 99.885. And now we're this confident that once we have treated the metal, that it's going to lower the HRC. And there's only going to be a small chance, a 0.0015 or 0.15% chance, 0.015% chance that it's going to be out of our mean value. Well, actually out of this value, the 57.3, not our mean, the 57.3 HRC that we were trying to prove. And that's how you're going to go about solving a one-tailed test. If you're looking for the mean to be greater than this area, you would do the opposite. So changing this value around and saying that it's going to be greater, we're going to be looking for just this area that's on top. So we want to find this area now instead of this one. So now this whole 99.88% is the rejection region that we're looking for, and this is the area that we're confident about it going up to. So the 99.885% is now our rejection region, and this is what we're going to accept, which is the 0.0015. Okay, now the third thing that I want to talk about is type 1 and type 2 errors. A type 1 error is basically when you reject the null hypothesis when it's true, and a type 2 error is failure to reject the null hypothesis when it's false. Type 2 is much worse, and I'll use a material breaking strength problem to kind of show the difference between the two and why one would be much worse than the other. So this is for material breaking strength. And in this, we're going to have basically one level where we want the material to break at. Anything under it would be unacceptable, anything above it would be better, but it's not really what we are trying to prove in it. So one way you can set this is with a chart. And for the material breaking strength, we're going to say it's going to fail or not fail. And on this side, we're going to list our null hypothesis, whether it's accepted or rejected. So this is HO reject and HO fail to reject. Okay, so for our first box that we're going to put on here, we're going to say that the material fails at its breaking point. So when it's supposed to break, the material breaks. For our second part in the box that's down below, since we're failing to reject our null, it's going to say that the material fails before its breaking point. And this right here is your type 2 error. And this is what we don't want to do. We don't want to have a piece of material that we say is going to break at this certain level, but it actually breaks before. I mean, you can see what bad things will come after that point. On the other side, we're going to say for our HO, if we're just rejecting it for our null, it's going to be the material does not fail at its breaking point. So this is actually a better thing, that the material is stronger than what it's rated at. So and this right here is our type 1 error. And the other point that we're going to have down here is the material does not fail before the breaking point. So when we reject the null hypothesis on here when it's not supposed to fail, we'll have a type 1 error. And this is the better of the two out of a type 1 and a type 2. On our null hypothesis, if we fail to reject it when it's basically not supposed to fail, we'll have failure before the breaking point, which is a much more serious error. So if we're going to have one of the two errors, we'd much rather have a type 1 rather than a type 2. And it's the same thing for setting up your null hypothesis. This is an easy way to figure out where your type 1 and type 2 errors come from. So that's basically everything that I'm going to go over on hypothesis testing for this time. Are there any more questions? And thank you.